Hi, my name is Dan Low. Welcome back to the parallel programming class. My name is Dan Low. So today I'm going to talk, in this video I'm going to talk a little bit more details about the CUDA API features. So when I say application programming interface, essentially these are the library functions you can use that comes from the CUDA package or any other libraries. So we call it API. It's the extension to the C programming language basically. Okay. So the regular C language obviously it does not provide APIs that support GPU computing. So you need to get a CUDA package to get this API to work. So it consists of language extensions, a runtime library will split into these. So we'll talk about the language extensions. So this language extension to target portion of the code for execution on device. Okay. So the regular C language obviously does not design to provide GPU computation. So you need these language extensions to cover the specific features of GPU. In a runtime library, split into the following: a common component, okay, providing the built-in vector types and the subset of the C runtime library in both host and device code. So in the example we have done earlier, we have the host code to compute the code, or we call it Oracle. And then we also have another piece of program that will be executed on the device. Okay, so some of the some of the components are common to both host and the device. Okay, then also there's a host component that controls and accesses one or more devices from the host. Okay, and the device component that provides device-specific functions, which will be executed on the device, which is GPUs. Okay, so language extensions. Let's take a look at the built-in variables. So we have a look at the block time. Okay. Block dimension, block time, and block IDX, thread IDX. So these are the built-in variables. You don't need to define them to use them. Okay, you can just use it because it's built-in in the CUDA compiler. So the CUDA compiler recognizes these variables. Okay, and there's a green time, GRIDDIM, that will give you the dimension of the grid that you defined. Okay, the X, Y dimension, and the Z dimension, as we studied earlier, the Z dimension is not used. Okay, in the grid specification. For the block dimension, we can use 3 dimension X, Y, and Z. Okay, and the block index is used, for the particular thread's block ID. Okay, and the thread ID is used for the particular thread's ID. Okay, the common runtime component mathematical functions such as pow, square root, CBRT, and the high part. The pow is some number to the power of something. Okay, like 4 to the power of 7. Okay, square root, you can calculate the square root. Okay, it's an SQRT function, and this cubic root, CBRT, is the function that calculates the cubic root of a number, and high part try to calculate the square root of x squared plus y squared. So these are the supported mathematical functions. So the best way to find out what they are and how to use them is go to the library manual. So here, I go to online library manual. You can go to this address, the developer.download.nvidia.com/rel/4_2/rel/toolkit/r/el/docs/online/index.html. So you can get to this page, and that is the CUDA 4.2 library documentation. Okay, so from there you can click on the modules. Okay, then from the modules you scroll down to the math functions. Okay, mathematical function, you click on it. So you can take a look at the single precision mathematical function, which is the floating point IEEE single precision 32-bit floating point supporting mathematical functions, or the double precision 64-bit IEEE 734 standard double precision with 64-bit floating point supported mathematical functions. So you can simply click on, let's say, double precision, click on it. Okay. Then the function will be seen CBRT. You scroll down, click on the CBRT. Okay, click on it. So it'll give you the prototype definition of CBRT. Okay. Then the device here that specify this function can only be executed on device. Okay, and that by the double or special return value for the function. So the return value will be of type double. Okay, then the function name is called CBRT, and then the arguments required to use this function is double x, and the function will calculate the cube root of x, which is x to the 1/3. Okay, x to the power of 1/3. Okay, and the return value x to the power of 1/3. Okay, then if it's a 0, then if x is 0, okay, then the CBRT will return 0. Okay, if x is infinity, positive or negative infinity, it will return positive or negative infinity. Okay, so by this way we know how to use this function, okay, in your program. And the other function we have seen is called you can scroll down, called HYPOT, right? HYPOT. HYPOT. Okay, here. So click on the HYPOT. Again, we will see the device or modifier that specifies this function can only be executed on GPU, and the return value type is a double. And the name is a HYPOT. It requires two variables of type doubles, x and y. Okay, so this function will calculate the length of the hypotenuse of a right triangle whose two sides have lengths x and y without undue overflow or underflow. So it will return the length of the hypotenuse square root of x squared plus y squared. Okay, so based on this, you can take a look at the rest of the functions, and note that you may have other options: single precision version of the program, a double precision of the single precision of the function supported. So that all the single precision will ended by f with the same function name. Okay, and the double precision will not ended by f. Okay, and there are some single precision intrinsics like 2_cost. So this is some faster version of the same function, but with lower precision. Okay, so now, there's also a function exponential ESP. Okay, the natural log base, and then also the log 2 base. It's ESP2, and there's a ESP M1, so ESP-1. So if you don't understand this function ESP M1, again, you go to the library search, okay, then you can ESP X1, right? ESP M1 here, right? Click on it. So it tells you what this function does and how you can use it. So it calculates the base e exponential of the input argument x minus 1. So which is returns e to the power x minus 1. Okay, in some computation we need to do this, to shift by 1 by taking the natural log. Okay, not taking the natural log actually, or by natural log to the power of x minus 1. Sometimes we need this type of computation, then you can call this ESP-M1 function. Okay. Then there's log 2, log 10, and log 1p is 1 plus, log function, sine function, triangular function, and then the inverse triangular function, and then the ceiling, floor, trunk, front function, etc. Okay, so a complete list again is here. So again, click on here, okay, to get a complete list. So when executed on the host, a given function uses the C runtime implementation is available. Okay, and these functions are only supported for scalar types, not vector types. So these are the scalar types of function. Okay, so let's take a look. Device runtime components, mathematical functions. Again, some mathematical functions, such as the sine x, have a less accurate but faster device-only function, such as this, and to underscore sine x. That's intrinsic. If you go back to the intrinsic, you'll find that function, which is here. Sine function, not here. Let me see. SIN here, right? Calculate the first approximate sine of the input arguments. Here, this guy. Okay. So these are as the first approximate sine of input argument x function. Okay, measured in radians. Okay. And similarly, you can have a faster version of the power function, the log 2, log 10, exponential function, sine, cosine, tangent function. Okay, so in some cases you don't need that high precision result. You can get this, to trade the you can trade the precision with speed. You get a better performance. The host part of the runtime component provides functions to deal with device management, for example, memory management, error handling. Okay, and use the device management, such as you can create threads, threads based on a kernel. That's device management. In memory management, you can allocate dynamic memory, to store the arrays. As it's been seen in our earlier exercise. Okay, and that error handling is something wrong. You want to find out what's wrong. Okay, so that will give you the error message or error code. So based on the code, you can try to see to find some clue about the bugs. And initialize the first time runtime function is code. So runtime component will first be initialized the first time some function code. A host thread can invoke device code on only one device. So multiple host threads is required to run on multiple devices. Okay, it's because one host thread can invoke device code only on only one device only. Okay. Device runtime component synchronization function. So we use a sync threads to synchronize all the threads in a block. Okay, remember that the threads sitting in different blocks. cannot be synchronized. Okay, only the threads in a block can be synchronized. So once all threads have switched to this point, executing resume normally. So you want to make sure all threads eventually will call this function. What happens is if a thread calls this function, it will wait there until all the threads in the block call the function. Then all the threads will be resumed. So this will be used to avoid RAW, WAR, WAW headers when accessing shared or global memory. We'll talk about these shared and global memory later. The RAW, that means some of the memory area you want to read the data within after somebody write data to it. Okay, so obviously if somebody write the data first, then you will read the updated data, not the old data, which is not what you want. So what you want is you read the old data first before somebody can write to it. This is called RAW. And on the other hand, the WAR is you expect that somebody will write data to a piece of memory, and after that you read the data for it. So obviously, if you try to read the same piece of data from the same location, the particular location first, and then if somebody didn't write to it, okay, then you may read some old data, which is not what you want, the causing error. WAR is some that you write, you expect to write something to it, and after that somebody will write to it. Okay, so obviously you don't want to swap the order and somebody write first. Okay, instead of you. So you tend to write, you have to guarantee that you write first and then somebody. So that is dependency, the ordering you want to guarantee. So in that case, you need to synchronize the threads. And allowed in conditional constructs only if the conditional is uniform across to entire thread block. So we'll talk about that. This is more advanced topic about the conditional construct, like if then else. If that's the case, then your threads may not be synchronized, or your threads may create some deadlock because some of the threads may not go to the synchronization point. Then all other threads waiting there may not have a chance to get out of the synchronization point. Okay, so we'll get into detail about that later. So that's all I have about the APIs. Again, if you need more information, you can go to this. Okay, so now let's get to another set of slides. Okay. Chapter 5. Okay, so chapter 5 is a little bit more detail about memory system. Okay, so let's take a look at the CUDA memory models. So first, let's take a look at the G80 implementation of CUDA memories. So here we got the host, which is your CPU, that communicate to the device in this rectangle, and within the rectangle you got a global memory, okay, and the constant memory, okay, global, constant memory, they're all global, okay, and then within the block of threads, you got the shared memory, you got registers, okay, and the registers belong to a particular thread. Shared memory, however, shared among threads within a block, okay, and global memory, constant memory, obviously shared by all the threads in blocks, okay. So that's basically all the memory hierarchy in the CUDA memory. So each thread can read, write per thread registers So these registers once belong to the thread. Only the thread can read write access to the thread to the registers here, and this thread can only access to the registers that belong to it. Okay, and read write per thread local memory. There's a thread local memory not shown here. Actually, this is a thread local memory. Okay, local memory, and this registers. Okay. So the thread local memory it's only it's private to a particular thread. Okay, and registers also private to a thread, but registers much faster than the memory, the per thread local memory. Okay, the shared memory on the other hand is shared among all the threads in the block. Okay, all the threads in the block. So in a way that it is slower, okay, than the per thread memory and registers, okay, but it's shared among all the threads in the block, okay. And there's a read-write global memory here that's shared among all the threads in the blocks, okay. Similarly, for the constant memory, it's only read only, okay. It's shared among everybody, but it's read only. Okay, so it's faster, a little bit faster than the global memory. Okay, so based on the access speed, okay, from the slowest to the fastest, it's actually from global memory, constant memory, okay, faster, and then shared memory, local memory, and registers. Okay. So registers are fastest memory for the thread to access. Okay. So based on the CUDA variable type quantifiers, we can specify what variable type will be, whether it's local, what storage will be for the particular variable. So for example, you can specify local variable using the device local modifiers. That will specify this integer variable, local variable to be local. So the memory here, that's local memory. The scope is to what extent the variable can be accessed. So it's within the thread. Okay, the local memory is within the thread. And lifetime is when the thread is live, is the variable is accessible. The thread dying, the memory gone. Okay. Then the second one is shared variable, the device shared. Okay, use these keywords or modifier. You can modify this variable to be shared. Okay, so the memory is shared variable, and then the scope is per block. Okay, the shared memory is the block, and the lifetime is block. Once block is there, it's there. Its block is gone. It's gone. Okay. Then you can also use just device without local or shared. And then now that case you will specify a variable to be global memory, and the scope is grid. All the threads in blocks, okay, can access. And then lifetime is application. Once the application is running, the global memory is there. Okay. And then the last one is the constant memory. Okay. You can specify using the constant keyword with a double underscore, ended by 2 underscore. Okay. And then put a constant there, and then there's constant memory. Okay. The scope is grid and lifetime is application. So the device is optional when used with local, shared, or constant. Okay, device. So that means when you say local, you actually don't need to specify device. By saying the local, it's device memory. Okay, share, same thing, constant, change, same thing. Okay. So automatic variable without any quantifier reside in the register. Okay, it's an array that reside in local memory. Okay, so if you don't specify anything, a variable is actually sitting in the register, for the thread. Okay, and if you specify an array, then array is it's gonna be stored in local memory. Okay, and if a local memory is also private to the thread. Okay, so local memory is private to the thread. Okay. So where to declare variables? Can host access it? If the host can access it, that is the outside any function that's global constant, global and constant. Okay. If the host cannot access, then it gotta be in the kernel. Okay. So it's registers, shared, and local variables. Okay. Variable type restrictions. Pointers can only point to memory allocated or declared in global memory. So for the local memory, we can use pointer. Okay. Or the register, you can use a pointer. Okay. Only the global memory variables, you define it as global, then you can use pointer. Okay. So allocated in the host and then pass to kernel. For example, we use this, right? This pointer, that's global. So global memory is allocated in the host, allocated in the host and then passed to the kernel. Okay, so it's pointer. Okay, obtain the address of a global variable like this. Okay, the global variable float, then you can get the pointer to that thing. Okay, a common programming strategy is this. Global memory resides in device memory, DRAM, much slower access than shared memory. Okay, so a profitable way of performing computation on the device is to tile data to take advantage of the fast shared memory. First, shared memory is shared among the threads in a block. Okay, so we want to load the data from the global memory to the shared memory, and then all the threads will do the computation. Okay, so we're gonna partition the data into subsets that fit into shared memory. Well, since shared memory is small, so you don't want you cannot store too much data. Okay, so we're gonna handle each data subset with one thread block. Okay, by loading the subset from global memory to shared memory. Okay, then using multiple threads to explore the memory label parallelism, and all we have done. So we create a block of threads, and this thread will do the computation there. Okay, then performing the computation on the subset from shared memory, and each thread can efficiently multi-pass over any data efficient over any data element. Okay, and then copying the results from the shared memory to global memory. So that's the common programming strategy. So this strategy basically, you want to avoid too much access to the global memory, because global memory access is quite slow. So what you can do is divide the data into smaller pieces. So each piece can fit in the shared memory in a block. So all the threads can work on that piece of memory. Okay, and then when you're done the computation, you put the data back to the global memory. Okay, that's the common programming strategy. And then the constant memory also resides in device memory, DRAM, much slower access than shared memory, slower. Okay, but it's cached, so it's high. It's actually better than the global memory. Okay, so it's high efficient access for read-only data because it cannot modify it, but you can put some read-only data there. Okay, carefully divide data according to access pattern. Okay, access pattern like read-only. Okay, then we'll put into constant memory very fast if it's cached. Okay, and then rewrite shared memory within a block, shared memory fast, and rewrite within each thread. And then those registers very fast, but the size is small, so you can see the you cannot put everything to the registers. You can see the put it somewhere if you don't use it that often. So you need to put the frequently accessed memory variables into registers, and rewrite input the results of global. Very slow, very slow. Okay, So for the textual memory matching, you can take a look at the NVIDIA document. So for GPU atomic integer operations, the atomic operations are integers in global memory, such as associated operations, unsigned, ints, addition, subtraction, min, max, and or, exclusive or, increment, decrement, exchange, compare, and so on. These are the atomic operations on integers in global memory. So that's atomic. Atomic means this instruction cannot be further broken into smaller sub instructions. So it's called atomic. So once the instruction can execute it, nobody can take away its data or its instruction. So that's called atomic. So atomic instruction will be guaranteed to be done without any other risk condition. And to support its atomic operations, the hardware requirement to have the compute capability higher than 1.1. Okay, so that's pretty much all I have about this for now. So I'll stop here, then we'll talk about the matrix multiplication using shared memory next time. Okay, good luck.